Thanks to the organisers for giving me the opportunity to talk today. And thanks for organising the conference. I know a lot of work goes on in the background to make these things happen. So my name's Simon Campbell, and today I'll be talking about the evolution of lithium in low mass stars. I'll do this by combining GALAH data with Gaia, asteroseismology, and also comparing to stellar models. And I hope to convince you that we have discovered another lithium problem. Okay, but first, I'll just have the last couple of years I've been putting a climate slide at the start of each of my talks because it's such an urgent crisis right now. So here I've got, I thought I'd go and look at the CO2 observations, so empirical data, because one of the questions that's sort of around at the moment is how much did the emissions go down in 2020 because of the pandemic? And so we have global CO2 abundance in the atmosphere versus time. The red line shows the seasonal variations and the black line is an average. And so I've highlighted 2020, and basically the takeaway message is that nothing changed, at least nothing detectable changed. It just keeps going up. So not too good. Back to the stars. So I'll start my introduction just by talking about the mystery of the lithium-rich giants. So about 1% of giants are found to be lithium-rich, which, and I'll explain the definition in the next slide. But basically it's if your A lithium is greater than 1.5 dex. Some have much more than that. So these are known as super lithium-rich stars. So we've known about these lithium-rich stars for more than 40 years now, but we still don't have a really good handle on how the lithium's produced. There's lots of models have been made. So for example, planet engulfment, rotationally induced mixing, binary interactions, but we still really don't have a good handle on it. However, there's been a really sort of key advance in this field in the last few years, and that's been thanks to Gaia and asteroseismology. So over on the right here, I've got CMD, sort of, and there's a big background CMD. This is from Casey et al. 2019. And over plotted is about 200 lithium-rich giants. And so what we can notice there is that they really are all around that clump region. So this is the core helium-burning phase of low mass stars. So this is pretty new that it's really isolated, and looks like something like 80 to 90% of the lithium-rich giants are there. So back to that definition of being lithium-rich. So it actually goes back to some old stellar models by Iben in 1967. So he published a paper back then that showed that when the star moves from the main sequence and becomes a red giant, so through the subgiant branch and towards first dredge up, the lithium decreases by more than a dex. So I've got a little schematic here. This is my little main sequence star. The solid colors that I'll show are all just convective envelopes. And so this star in the main sequence has say a lithium value of something like 3. But inside is so hot that it's burnt all the lithium. So it's basically 0 inside. And so what happens when it evolves to become a subgiant branch star, the star expands, but also the convective envelope deepens in mass. And so this mixes up some of that 0 lithium material into the surface. And that's why the lithium gets diluted and drops. And so this continues onto the RGB proper. So this is sort of right at the bottom of the RGB, the first dredge up phase, where the envelope is at its maximum sort of extent inside. And by that stage, you have a lithium of something like 1.5. And that's where the limit comes from, this for lithium-rich red giants. So all phases of evolution over that should have less lithium. And if you find one with more, then it's lithium-rich. So that's been used for ever since. And I think it needs revisiting because of the new information that lithium-rich giants are actually not RGB stars, they're red-clump stars. It may still hold, but it's worth checking. Okay, so we do see this dilution in real stars. This is a study by Lind et al. In 2009. It's a global cluster, just as an example. So we have magnitude here and lithium along the bottom. And you'll see a lot of these plots have got lithium reversed. So here's the main sequence, constant lithium, and then here's the dilution episode, and then it's constant again along the RGB. So models wouldn't predict any more reduction in lithium, but observations have shown us different. There's actually another fast lithium depletion phase after the RGB bump. So the bright RGB is destroying lithium for some reason. And so modelers try to explain this, theorists try to explain this. To cut a long story short, there's lots of models out there, lots of theories about how it happens. Probably the most popular one is thermohaline mixing, and that's what's used in this plot on the right. This is from the Monash group. And there's a few different stellar codes in here. And so basically what you need to do is to destroy lithium is to deepen the envelope more than a standard model would say. So you take the bottom of the envelope to a higher temperature, so high enough to destroy lithium. It also affects other elements, but I'll just talk about lithium here. Now, so here we have the dilution phase, going to the subgiant branch. Here's the bump, and then we have this burning. So that's the second lithium reduction phase. And so we have models that explain it all, which is nice. So then along came GALAH Li, and this was great. It had more than 100,000 stars with lithium abundances, and it's high resolution survey, so you can get down to fairly low abundances as opposed to other surveys. Combining this with Gaia, you can get good luminosities, as we've heard earlier today as well. And over here, I'm put a box around this red clump overdensity. And this is our red clump sample, which I'll talk about on the next slide. And so just as a reality check, so asteroseismology is very good at separating the RGB and red clump. So we cross-reference this with a inferred seismic parameter catalog from Yuan Sen Ting, just to check contamination with RGB stars. And that contamination's pretty low, which is good. So confronting GALAH with models, or models with GALAH. So here we have that same plot again, luminosity, lithium along the bottom. Here's one of my models that has the dilution as you go to subgiant branch, and then you have this RGB deep mixing burning. Now after that, the stars have low mass stars have a core helium flash, and this terminates the RGB branch, so the RGB. And then they suddenly drop down to the red clump. So this happens very fast, this drop. And so the stars end up down here. And because you've had all this depletion on the RGB, your red clump stars should have a lithium of something like -1. And they should be at this luminosity. Just move that over there. Over here, I've got the RGB lithium rich line, the classical one. And so
2 minutes, Simon.
Thank you. So here we're proposing the limit for red clump stars. So because they have this extra dilution, this extra reduction in lithium, then a red clump star should be considered lithium rich or lithium enhanced if it's above this line of something like -1. And so we thought, okay, we'll have a look at GALAH. We expect maybe we'll find a few lithium enhanced stars, lithium enhanced red clump stars, some extra lithium rich giants. But this is actually what we found. So it turns out that all the stars were over here at about +0.7 dex, which is a long way from this model prediction of -1. So it's something like a factor of 40. And it seems to be most stars, if not all. It depends on the sampling. But this was a bit of a surprise. So I was coined this term last night, calling this the red clump lithium problem, maybe. So it's another lithium mystery. And because it seems to happen to most stars, or maybe all, then there seems to be a regular lithium enrichment phase. And this happens, so instead of the stars going from the top of the red giant branch here, straight down, they seem to go in this direction. So this implies a lithium production phase between the late RGB and red clumps stage. So it could be happening at the flash, could be in the late RGB, or it could be on the early red clump. And then to put the classical lithium-rich giants in context, they're over here. So GALAH picks those up very nicely. And they're red clump stars as well. They've got the same luminosity as I showed earlier. So they look like that they're the tail of the distribution of this sort of mainstream enhancement of lithium. But that's sort of yet to be determined. But just at first glance, it looks like there's a peak of lithium enhancements around plus 0.7, and then there's this long tail, and some stars seem to get a lot of lithium. Or they might be the very young lithium-rich stars, and we had a paper on that recently, which I don't have time to go into. So just as a conclusion, we have a new problem, red clump lithium problem. And I'd just like to say a huge thanks to all the past and present GALAH team members, because I know there's been a massive effort over the last 10 years at least, I'd say. And it's really the people that have made this survey a huge success that it is now, as evidenced by this conference. Thank you very much.
Thanks, Simon. Yeah, great to see this data actually being helpful, also for modelers. Great. Do we have questions online? Because I definitely have one. Sarah's asking, are you working on a model that produces lithium?
Yes, and so after that paper was published, go to my appendix. So as soon as it was published, a few modelers, including me, but I'm a bit slower than the others, published a couple of papers trying to explain it. And so they both invoke one invokes very exotic physics. So this is the Mori et al. Paper. And they can't quite make enough lithium because they can't, changing their parameters, they can't change them that much. The Schwab et al. Paper can reproduce it, but that's also ad hoc. So it's just sort of like an extra mixing thing. So we don't know where this extra mixing comes from. And also there's parameters in there, so you can actually produce as much lithium or as little lithium as you want. So we don't have a sort of self-consistent model yet, but yeah, we're working on it as well.
All right, cool. We have one more hand raised online. Evan, if you want to go.
Thank you. I don't mean anything negative by this comment, but are those truly genuine, bona fide, gold-plated lithium abundances? Like those are, is there any chance that this is just a pileup of upper limits?
Well, the referees had of course, that question as well. A lot of them are the Canon abundances from GALAH. So I've got a few plots on here. I have one from Kirby 2016. Let's see. Sorry, just flicking through here. So we went through a few sort of reality checks. So this was comparing with the Gaia-ESO survey, which is a high resolution survey, spectroscopic survey. So we cross-matched between GALAH, and we only came up with a couple of red clump stars. So this is the GALAH Gaia-ESO survey, red clump stars, the squares, and they are sitting sort of straddling around that peak. So statistically, that's where you would expect to find a couple, and they seem to have very consistent abundances with that survey. And the LAMOST is low resolution, so you can only get the really lithium-rich ones. So they're red clump stars that sort of much more lithium-rich, more like super lithium-rich. I'm not the observer, so there's also some extra observations from Kepler. It's a Kepler sample of very high resolution, and also there's open clusters. So this is Karlberg et al. Cluster sample, and they all seem to be, actually I've got that in this plot. Here we go. So this is the plot from the paper. So we sort of backed it up with so open cluster averages here. So there's 3 open clusters. And also this is a very high resolution Kepler sample. So they absolutely know that you've got red clump stars, and think the resolution was 100,000. So
I see.
Yeah.
Thank you.
No worries. Yeah. Also, yeah, coming to the rescue of GALAH DR2, we've actually done the cross-check of DR3, where we have really measured all of them with spectrum synthesis. And even though DR2 was done with the Canon and possibly was extrapolating, the agreement was very, very striking. So yeah, we were also surprised to see that the Canon actually worked for lithium that well. But yeah, it's great to see this. All right.
Good to hear.
Yeah, yeah, exactly. All right.